Hey there, and welcome to my lesson on how we're going to be using integration to find the volume of a rotated figure around some axis using what is known as the disk and the washer method. So a disk, think of it like a quarter. It's essentially going to be just like a very small kind of cylinder like that. And a washer is basically the same thing. It is kind of that circular part, but we have an outer radius and an inner radius. So uh, with the disk method, we're basically going to just be working with a very small cylinder that we can find the volume of that, and if we have an infinite number of those things kind of, stacked up in an interval, we can say that that's going, using integration, that's how we can get the volume. With the washer method, it'll be similar to the disk method, but because we have that interior region that's not going to be used, that's not going to be included in part of the interval, we're going to have to find the volume of the cylinder using the outer radius minus the volume from using the inner radius. Let's see, I'm not real sure what there was information here that I wanted to kind of illustrate or highlight, so let's just look at it real quick. Earlier we used integration to evaluate areas of region. Well, yeah, that would be just general kind of integration, the area under the curve, fundamental theorem of calculus. Now we're going to look at integration to find volumes of solids. Well, we've already done a little bit of that. Formed by rotating region around a given straight line. And for the time being, that's basically just going to be either the x or the y axis. If a region in a plane is revolved around a line, the resulting solid of revolution is, and the line is the axis of revolution. The simplest such solid is going to be a cylinder, which I told you was a disk. And that's going to be the first one that we're going to take a look at, which is formed by revolving a rectangle about an axis adjacent to the side of a revolving a rectangle about an axis adjacent to the side of, yeah, to the side of the rectangles. I read that wrong. So here, hello, computer, are you with me? There we go. For example, consider the region that we have here. Uh, the region that we have here, bounded by the x-axis, the y-axis, and the line x plus 3y is equal to 6. Now imagine rotating that kind of triangular region around the y-axis. So we're going to take this triangular region and we're going to rotate it, whoops, around the y-axis like so. Clockwise, counterclockwise doesn't really make a difference. We're just rotating it 360 degrees, and you can imagine, like, imagine if you had like a piece of paper taped to a stick, and you just ran the stick in between your hands. The paper would move fast enough that you would be able to visualize the cone that would be created. Now the cone, we can find the volume of a cone. In this case, we know the radius, we know the height. We can find the volume of the cone using simple geometry, 1/3 pi r squared times the height of the cone. But essentially what we're going to be doing is we're looking at it in terms of, and I don't remember if there is a, yeah, there we go. Essentially what we're looking at it is we're taking kind of that little rectangular slice here. We're going to take an infinite number of those in that region and twirl them around the, we're going to twirl them around the y-axis. And let's see, I want to go back for a second because I think somewhere it kind of told us what the volume was going to be. Yeah, volume 1/3 pi r squared times height. In this case, indicates that the volume of that particular cone should be 24 pi cubic units. Well, now what we're going to try to do is we're going to try and recreate that same value with calculus and integration. Okay? Because not always are we going to have a nice, simple kind of geometric shape with which to work, but it is a good place to start because we're able to kind of have something that we can compare our answers with. Did we do do we get the same answer both ways? And yes, then the approach is valid. So what we're going to be doing, again, we're just kind of taking an infinite number of those little rectangular strips where delta y is going to be very, 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 very small, the change in y. And when we take the integration of the infinite number of rectangles contained in that region, circled around, using the volume formula, then we can get our same answer using integration. So here, this was the information that was given to you. Write the volume of the cone as an integral on the interval from 0 to 2. And one of the things that it doesn't tell you here in the problem, but it does kind of tell you earlier, is that we're rotating around the y-axis. Okay? So when I rotate things around the y-axis, we want things solved in terms of y. I'm sorry, not solved in terms of y, solved in terms of x. Okay? So that's what I'm going to do here with the expression that I have. I'm going to take this expression for the line, and I'm going to use that, and I'm going to solve it in terms of x, which in this case would just be x is equal to 6 minus 3y. Okay? So that 6 minus 3y, that effectively, what we're, again, the formula for volume in this case of the cylinder, the volume of the cylinder, pi r squared times the height. Well, in this case, r is going to represent what we have for x, and h is going to represent what we would have for the change in y, delta y. So that's going to be helpful for us to setting up the integration problem. Now the pi itself, that's just a constant. So the constant that we have for the volume formula, we will keep that out of the integral when we do our problem here. So if I wanted to find the volume, if I wanted to take that volume formula and translate it into something calculus related, I'm going to take the constant of pi, leave it outside of the integral, and in this case they're telling us we're doing it on the y-axis from 0 to 2, so that's the interval that we're looking at, 0 to 2, and we're going to say, just taking the volume formula, r squared times h. Well, we can rewrite that 0 to 2, r squared, in this case the radius is the expression that we had in terms of x. So we can replace r with x squared, and we can replace h with delta y. And the final substitution that we can make here, and this is only for illustration purposes, this isn't something that I would expect students to show each and every substitution here. Here we're going to go 0 to 2. So now I'm going to take that 6 minus y, and I'm going to substitute that in for x. Now I'm going to put that in parentheses because we are squaring it. So 6 minus 3y, quantity squared, dy. So that, and volume, where it says write the volume of the cone as an integral from 0 to 2, that is what we just did. Now it's actually asking us to find the volume of the cone. Now we could use U substitution here, but I don't think this one's really going to be worth doing U substitution on. It's very easy to expand this one. So now we're going to just go ahead and let's expand the binomial that we have in there. And when I do, putting it in standard form with the y squared first, I'm going to get a positive 9y squared and minus a 36y and then plus a 36 dy. And now we take the antiderivative of each part. So I'm going to get pi multiplied by, let's see, that'll be 3, a third of 9 is going to be 3y cubed. That'll be 1/2, so that'll be minus 8 14 y squared, and this would just be plus 36 x, nope, y, I'm doing it in terms of y. And we're evaluating it from 0 to 2. And the 0 here really makes me happy because I know if I substitute 0 into those things when I do my difference of the two substitutions, well, the 0 is just going to be nothing. So I don't need to worry about substituting the 0. I'm only going to substitute the 2. So here I'm going to get pi times 3 times 2 cubed minus 18 times 2 squared plus 36 times 2. And again, minus 0 if you need to have anything there. And when I do that, 8 times 3 is going to be 24. 4 times 18 is going to be a negative 72, and then a plus 72, and we can see that those two are going to cancel out. So we're left with just the 24 inside of the brackets. 24 times pi is 24 pi cubic units, which again verifies that, one, did we get the correct answer that we were looking for? Yes, but by getting that correct answer, we are validating what we had here for our calculus integration problem. Okay? Now, did I need to do calculus for this? Absolutely not. We know how to find the volume of a cone pretty easily, but will we always be able to find the volume of a cone, or will we always get a cone that we can use to kind of help us with the formulas? So we're going to look at these all with an integration mindset. If we need to, maybe we could kind of fall back on geometry to verify that we're doing our calculus correctly. But here, this is kind of illustrating essentially a little bit more in detail what the disk method is doing. You're kind of taking that small rectangular region, rotating it around an axis, which is creating that small cylinder, which is why we're using the cylinder formula for volume. When finding volumes of a solid of revolution, it's important to focus on what happens to each individual strip as it's rotated. A thin slice or strip can be horizontal or vertical, and we've seen that with the cross-sectional volumes that we've done in a previous video. Depending on which way you're rotating around the x-axis or the y-axis tells you whether you take your equation and solve it in terms of x or y. The volume is sliced vertically. We would have something like that where it's going to be rotating around the x-axis. And generally speaking, here, this W, the width of the disk, that W, that could be the change in Y, or it could be the change in X, depending on which way you're rotating. So for instance, in the picture that we have, we're rotating vertically. So the width of the cylinder, the height of the cylinder, where they have the W, that would be delta X, or dx, or dy when we do our integral. Excuse me. Here, it's telling you the horizontal axis of revolution. Solve for y in terms of x if you're doing a horizontal axis of revolution. Basically get x by itself, kind of like what I just did a moment ago in that first example. And if you're rotating vertically, you solve for x in terms of y. No, I did that backwards, I think. But we are going to, depending on which axis that we rotate around, have to solve some expression in terms of either x or y, depending on which way that we go. And here, set up and evaluate the integral that gives the volume of the solid by revolving the region about the x-axis. So here, they're giving us just negative x plus 1. So that's a pretty straightforward linear function. We're going to have a y-intercept at 0 and 1. and it's going to have a slope of -1, so it'll kind of do one of those things here, and it'll have an x-intercept of 1 and 0. And we're going to take that region, and so set up and evaluate the integral that gives the volume. It's not being super specific. It should kind of really indicate that it's going to be contained between that line, -x plus 1, and the x-axis and the y-axis, or when x is equal to 0 and y is equal to 0. It really should kind of illustrate that because the volume, the region that we're going to be rotating, the region that we're going to be rotating is going to be this region here. That's what we're going to be rotating, and we're rotating it about the x-axis, so it's going to be kind of going this way, that way around the x-axis. And because we're going to be rotating something around the x-axis, this bit here, this would represent the radius. They used a big R for radius. Okay, so we'll use a big R for radius, which, if you notice, is vertical, meaning it's the same thing as something in terms of y. So because we're going to be rotating this around the x-axis, we want our formula that we have solved in terms of y, which, hey, it just so happens to be that way. So generally speaking, to find the volume, I'm going to say the volume is going to be pi multiplied by whatever the integral is from a to b, whatever the interval happens to be. And then we're going to take the radius of either x or y, and we're going to take that and square it and then multiply that by the change in either x or y. Delta x, delta y. That's just the volume formula that we were working with. So in this case, the radius r is y, which is -x plus 1. So I'm going to take that -x plus 1 and drop it right in here. Okay. So let's see what we get. Now, what is the interval? The interval should be from 0 to 1, basically. Okay, that'll work. So we have our constant pi times the integration from 0 to 1, and of course I like the 0 because it means we don't really have to subtract the lower bound stuff because it's all going to be 0. But in parentheses, I'm going to say -x plus 1 quantity squared dx. And like on the last example here, I think this one is worth just expanding the binomial to see what we get. So pi times the integration 0 to 1. So when I expand this particular binomial, I'm going to wind up with x squared minus 2x plus 1 dx. And now we can do our antiderivative. So I'm going to get pi multiplied by 1/3 x cubed, and this would be 1/2, so that'll be minus x squared, and then plus x evaluated from 0 to 1. So substitute the 1 in there, and basically we're going to just wind up with 1/3 minus 1 plus 1. So let's just go ahead and write it out. I'm going to wind up with 1/3 minus 1 plus 1, and you're going to see that those two guys are going to cancel out. So I have pi over 3, or 1/3 pi, depending on how you prefer to write your fractions, for the volume of that particular figure. And of course, you could check it. This one, if we rotate it, will create another cone, blanked out there for a second, another cone that you could, find the volume of. I think I muted my headphones. Hopefully, I'm going to cross my fingers that things are still recording here. All right. So where am I at? I'm going to just check my time here. 19 minutes. Okay, so we'll come back in about 20 minutes when I check the video and audio, and hopefully everything will work. But that is, now here, this is what we were kind of looking for on the last example, where it's just kind of, giving you the clear boundary here. And I encourage you to go ahead and see if you can, pause the video at this point and just try working it out and see what you're able to get. But presuming that you've worked it out, let's go ahead and give you the opportunity to check yourself. We have three functions that we're working with. We have y is equal to x. I'm sorry, y is equal to the square root of x. So it's going to do one of these things here. And then we have x is equal to 0, which is the y-axis, and x is equal to 4. So I'll just say this is when x is equal to 4. So the region that we are going to be rotating, that we're going to be trying to find the area of. Now this one is not going to be a straight cylinder. This one would be more bowl-shaped, kind of like a top or something, because if you take it and you rotate that around, because of the curvy portion of the square root function, that one's not going to be an exact cylinder. I'm sorry, an exact cone. So not really going to be able to find a geometric equivalent of this without just approximating it maybe with a cone. But same idea. Let's go ahead and see what we're going to be doing this. We're going to be revolving it around the x-axis again. So, I don't want to keep using my crayon here. I just wanted to have the crayon to show where the highlighted region is. So we're going to be rotating it around the x-axis again. So that means my radius, just pick a spot, and that's going to be the radius, and the radius in this case is vertical, so that's going to be equivalent to whatever y is. So that means because we're revolving it around the x-axis, we want everything solved in terms of y. And in this case, y is equal to the square root of x. So when I go to my integration, volume being equal to pi times the integration from the lower bound to the upper bound of the radius, and in this case we are doing it around x, so that would be squared dx. We can take the radius and just substitute the square root of x into it. So the only thing that I really want to know is what's the interval going to be. And the interval, according to the way that we graph the functions, we're going to be when x is 0 to when x is 4. So that's my interval from 0 to 4. And now we have all the information that we need. So I'm going to say volume is equal to pi times the definite integral from 0 to 4 of the square root of x squared dx. Well, simplifying the square root of x squared, that's just going to be x. So we have pi 0 to 4, that's just going to be x, 4, dx. So now we can find the antiderivative, and in this case we're going to have pi times 1/2 x squared, and we're evaluating it from 0 to 4, and of course I like the 0 because when we do the substitution with 0 for the lower bound, it's all going to cancel. So I'm really only going to substitute the upper bound stuff, but I'm going to take that constant. I'm going to go ahead and take this constant out and pull it out of the brackets here, because we can just factor that constant out. And so that is going to give me pi over 2 times 4 squared minus 0, 4 squared minus, I guess I should technically have that in a bracket like that. So that would be 16 over 2, which would just be 8 pi cubic units. And there's the volume. Okay? So again, moving on, let's try the next one. Here we're going to take y equals x squared, and we're going to revolve it around the x-axis. So if I'm revolving around the x-axis, I want things solved in terms of x. So I'm going to take this, take the square root of both sides, and that means that the square root of y will be equal to x. Okay? Now this particular one, if I graph it, y is equal to x squared, that's just the quadratic parent function. So it's going to do kind of one of these things here. And so if we're revolving it around the y-axis, this is when y is equal to 0 and y is equal to 4. So we'll just put a 4 here and a 0 here. And based on what I know about the parent function, when y is 4, x is either going to be a positive 2 or a negative 2. And we're going to take this thing and we're going to revolve it around the x-axis. So imagine that parabola kind of spinning around. Now again, we're still doing the disk method. So this essentially is your radius. And in this case, the radius is going to be whatever x is. That's why we wanted to solve our values in terms of x. So in this case, that is the square root of y. So again, the volume that we have, volume is equal to pi multiplied by the definite integral. And typically for when we revolve it around the y-axis, they kind of like to do a c and a d here. R of y, quantity squared, dy in this case, because we're revolving it around the y-axis. So substitute. And we'll say pi times, now the interval was given to us to be 0 to 4, and the radius in this case is the square root of y squared, dy, that kind of looks like a cube, but dy, and simplifying the square root of y squared, 0 to 4 would just be y, 0 to 4 dy. And I think you're kind of seeing a pattern here, because let's go back and look at the last problem. We're kind of seeing the exact same thing at this point here in the last example as we did on the last one. And it kind of makes sense because this function that they gave us, this function that they gave us here and this function that they gave us here, they're inverses of each other. So here we have the whole parabola graph as opposed to, just half of the sideways parabola here, but we're still revolving the same thing, so we should wind up with the same volume, the way things are looking. So take the antiderivative, and in this case I'm going to get the 1/2 y squared, and again we're evaluating it from 0 to 4, so again I'm going to pull out the constant, factor out the constant 1/2, and that'll give me pi over 4. Nope, pi over 2. I don't know where I'm getting 4 from. Pi over 2, probably because I was thinking about what I was going to substitute. So we're going to get 4 squared minus 0 again, and that's just going to be 16 times pi over 2, which will simplify to be 8 pi cubic units. So there we go. That's pretty interesting. The next example here, y is equal to e to the x. So we're getting a very interesting function now, or I should say more interesting than what we have. We're revolving it around the x-axis from 0 to 2. Okay, so what do I know about the exponential function? The exponential function goes through the point 0, 1, and excuse me, it's going to have some kind of exponential curve going this way. We're stopping it at 2, so that is the interval. So essentially the volume that we are looking for, is kind of going to be this stuff here that's going to be rotated around the x-axis. So we're rotating around the x-axis, meaning again we want things solved in terms of y. Okay, so again my volume is going to be pi times a to b r of x quantity squared dx in this case for the volume rotated around the x-axis. So what is the radius? So the radius here, that's the radius, which is y. That's my vertical axis, which in this case is e to the x power, we didn't have to do anything to get x to get y by itself. So doing my substitution here, I'm going to say pi. My interval was given to me to be 0 to 2 on the x-axis. The radius in this case is going to be e to the x power squared times dy, nope, dx, not dy. So simplifying this, we're going to get pi times the definite integral 0 to 2 of e to the 2x power dx. Now when I take the antiderivative of that, I'm going to wind up with 1 half e to the 2x power, evaluated from 0 to 2. Now let me just so I'm not making sure I'm not losing anybody, let's take a quick aside here. Why am I getting 1 half e to the x to the 2x power? Essentially, we're kind of looking at u to be 2 to the x power. So when I say du in this case, I get x dx. Nope, not x dx, 2 dx. 2 dx, which doesn't match the 1 dx that's left. So we get a constant 1 half du to be equal to 1 dx. And that's where that 1 half is coming from for the constant. A lot of ways that you can look at it when you're dealing with e to the power. A lot of times we wind up just taking the reciprocal of whatever that constant is. So that's why it's e, or 1 half times e to the 2x power, as opposed to with the just e to the 2x power is the antiderivative. But now that we've had that little aside done, again, I like my lower bound to be 0. That's always nice because substituting 0 just gives you 0 in this case. So here I'm going to say pi times, and I'm going to pull out that 1 half as a constant again. I'm going to factor that out, so that'll be pi over 2 times e. Actually, no, in this case, substituting 0 doesn't give me 0. Ugh, okay. So we're going to say 2 times 2 for x minus e times 2 to the 2 times 0 power. So I wind up with pi over 2, and that would be e to the 4th. And e to the 0 power will be 1. And that's probably where I'm going to just stop on that one. There's no reason to try and simplify that one any further. But that's where we're at for the volume on that one. Hopefully you guys are picking this stuff up okay. Because now we're going to be moving on to the washer method, and this is the washer method is going to be slightly more complicated because we do have that region that we have to remove. In geometry, when you did stuff like this, in geometry you might have had kind of a cylinder where you had this other kind of cylinder inside of it, and that was kind of removed, and so you'd have to find the volume of the outside cylinder and subtract the volume of that kind of interior cylinder where you kind of removed it, and that would be what was the difference is what the volume of the overall cylinder was. Well, we're kind of doing the same thing here, okay, except now instead of doing it with just cylinder minus cylinder, now we're using it with integration. And what we're doing here, so imagine that we had, this kind of weird shape. I don't know, maybe that's like a line for the g of x function, and maybe, I don't know, maybe it's a compressed quadratic or some other kind of polynomial function or whatever for function f. But essentially what we're going to do is if we took that and we rotated it around the x-axis, we would kind of create a region where we would have an outer cylinder, an outer radius. So we would go, let me go from here. If we rotated this around the x-axis, kind of like what the picture is showing us, This segment would represent the outer radius uh, of the function. Whereas here, let's pick another color here, this segment would represent the inner radius, okay? And that's why we're kind of differentiating with a big R and a little r. And we have to actually take the difference of them. So here, and here we can kind of see a little bit more what a washer looks like and seeing how we're getting uh, the difference between a big R and a little r. So a big R, in this case, you can think of that as the outer radius, and the lowercase r would be the inner radius. So let's see what we're going to end up with when we work some of these, work some examples out here. Find the volume of a solid formed by the region bounded by the graphs y is equal to the square root of x and y is equal to x squared. So those are inverses of each other, and we're rotating it about the x-axis. Okay, so because they're telling us we're rotating about the x-axis, that tells us that we want our functions solved for x. Okay, so let's do that with two of them. Well, first of all, let's graph them. Let's graph them and see what they look like. So let's graph this function in kind of that pinkish color. So the square root function is going to be something like this. And we'll do blue for this one. And if we were going to graph that one, I really only need to kind of stay on this side here. This is going to be that, and so the shaded region, the region that's contained between those two, that's what we're going to be rotating. So we're rotating this region, okay? And we are going to be rotating it around the y-axis. So we're going to take that shape and we're going to go around the y-axis like that. So that means from, let me go back to my blue color, this segment right here would represent the outer radius, which would be in terms of x, because that's that horizontal segment. And so that one, if I take that and I solve it for x, this one was y is equal to x squared, so take the square root of both sides. So in this case, x is going to be equal to the square root of y. So that's the outer radius. And the inner radius would be this one right here. This would represent the inner radius, which again is going to be in terms of x. And if I take the y is equal to the square root of x and I solve it in terms of x, that would be when x is equal to y squared. So now we have our inner and our outer radii. So let me pick a color I haven't used yet here. And the volume that we're going to be looking at, the volume is going to be pi times the definite integral. And where is our definite integral going to be? In this case, we're needing to see where does it intersect at? And they should intersect, because they're inverses of each other, they should intersect at 1 and 1. So my interval, and let's just put 1 here, my interval is going to be from when y is 0, and I'm not going to put a comma there, from when y is 0 to when y is 1. So 0 to 1, and we're going to do the larger the outer radius, and in this case, it's going to be in terms of y, and we're going to square that. And we're going to subtract the smaller radius also in terms of y, and we're going to square that. This integral is going to be in terms of dy because we're rotating around the y-axis. So the outer radius was going to be the square root of y, so I'm going to substitute that here. So I'm going to get the square root of y squared. The inner radius is y squared, so I'm going to say minus y squared, quantity squared, dy. Let's simplify those expressions. So we have pi, 0 to 1. So the square root of y squared is going to be a y, and y squared squared will be minus y to the 4th power, dy. And now let's go ahead and do the antiderivative of this integral here, because those aren't like terms, we can't combine them. So we're going to say pi, and this will be 1/2 y squared minus 1/5 y to the 5th, and we're evaluating it from 0 to 1. And in this case, I don't really have a common factor that I could factor out. I don't have a constant that I could factor out. But I do, again, kind of like the fact that I have a lower bound that's 0, because substituting 0 in this case will cancel out. Now I'm not going to shortcut this one. I will do this substitution of 0 just to illustrate it this time, because this is our first one where we have the difference of two things. So in this case, the upper bound will be 1/2 times basically 1 squared minus 1/5 times 1 to the 5th minus 1/2 times 0 squared minus 1/5 times 0 to the 5th. And that is the proper fully substituted things, but of course you're going to see all of this just goes to 0. So I'm really only going to be focusing on the stuff where I'm substituting 1, and that's just basically going to be 1/2 minus 1/5. And so 1/2 and 1/5, the common denominator is going to be 10. So that'll be pi times, so that'll be 5 over 10 minus a 2 over 10, which would be a 3 over 10. So that'll give me 3 pi over 10 cubic units for my volume. And there we go. That one, again, a little bit more complicated because you do need to make sure that, not only do you need to understand which variable are you having things solved in terms of, depending on which axis you're rotating around, but you had to be able to graph both of those, identify what the interval was going to be because it didn't give you the interval, and then from the graphs, identify what the inner and outer radius are going to be and substitute them correctly, in addition to all of the actual integration that you would have to do. But hopefully things are coming along okay for you. And here, this is our next to last example. So we'll go ahead and try knocking this guy out here and see how well we do. And again, feel free to go ahead and try pausing this, pause the recording and just see if you can work this one out in advance of me. But let's see what we have here. Find the volume of a solid between the two lines over the interval 0 to 2 revolved around the x-axis. Okay, so we're revolving around the x-axis, so we want things solved in terms of y. So let's go ahead and graph these and see what we end up with. 1/2 x plus x squared. So we're taking the parent function and we're shifting it up basically half of a space. So let's go ahead and let's graph these here. Let's do this one here. That's going to be the easy one to graph, like that. There we go. And then the other one, we'll do that guy in blue again. Let's graph this guy in blue. So let's just say, I don't know, let's just say that that is when x is 1/2, because it's going to be your y-intercept. And then we're going to have quadratic kind of going like that. And so the region, they're giving us our interval from 0 to 2. So in this case, I don't know, they're not really clear. I probably could have extended my parabola out a little bit more, but let's just say, for the sake of, let's just say that for the sake of simplicity, that this is where x is 2 is at. So the region that we're going to be rotating is going to be this stuff here. This is the region that we're going to be rotating, okay? And we are going to be rotating it about the x-axis, so we're rotating this way, so we want things solved in terms of y. So that means this, let me go back to my blue. That means that this segment here is going to be my larger, or my outer radius, which we're having it solved in terms of y, which in this case is just the 1/2 plus x squared. And we have, let's do here, pink. So this one here, that's going to be your inner radius. That's going to be your inner radius, which again is going to be solved in terms of y. And that one is just x. Okay? So let's see what we can do here for the integration. Again, we're going to say volume is equal to pi times the definite integral from 0 to 2 in this case of the larger radius squared minus the inner radius squared in terms of x, because that's what we're rotating it around. And let's do our substitution. So the larger radius in this case is going to be 1/2 plus x squared, or x squared plus 1/2 if you prefer. Doesn't really make a difference. 0 to 2, so this is going to be 1/2 plus x squared squared minus, and this one is just x squared dx. And I'm going to go ahead and expand these again so that I can kind of have something that I might be able to simplify. 0 to 2. And 1/2 plus x squared squared is going to give me, that'll give me an x squared. 1/2 and 1/2 will be oh, nope, not x squared. X to the 4th. And 1/2 and 1/2 will be plus 1x squared, and 1/2 and 1, I'm sorry, 1/2 and 1/2 will give me 1/4. And the x squared is just going to be x squared, but we have that negative sign in front of it, so it'll be minus x squared dx. So you can see that this x squared and this x squared cancel each other out. And so we have pi integral 0 to 2 x to the 4th plus 1/4 dx. So that's our simplified expression that we will now perform the antidifferentiation with. Pi, and that'll be 1/5 x to the 5th plus 1/4 x, evaluated from 0 to 2. And do your substitution. So we have pi. Again, we don't really have a a common factor that we can pull out as our constant here. But here I'm going to say 1/5 times 2 to the 5th plus 1/4 times 2. And substituting 0, again, in this case, is not going to matter. So I'm not going to write it this time. And let's see what we get. So 2 to the 5th is what, 32? So that's going to be 32 over 2, 32 over 2. And 2 over 4 will be 1/2. So that'll be 33 over 2. No. Oh, no. Somebody's yelling at me here. Probably somebody's yelling at me, rightly so. I wrote my denominator wrong here. This is 1/5, 2 to the 5th. So this will be 32 fifths. 32 fifths. And so now I would have to get a common denominator. So that looks like it's going to be a 10 again. So that'll be 64 plus 5, that'll be 69 tenths. So 69 pi over 10 is going to be my final volume for that rotated figure. All right, guys, hope we're going strong with this. We got one more to do. Drill a hole. We're going to drill a hole through a metal sphere, which has a radius of 5 inches. The hole has a radius of 3 inches. What is the volume of the resulting metal ring? Okay, so we have a sphere. So if we look at it as a cross section, that's going to be a radius, or like imagine you slice that sphere in half. We're going to have a radius of 5 inches. So this would be -5. I know we don't have negative inches, but still. We're not it doesn't say it's translated in any way, so let's sketch it. So if it's a circle that's centered at the center, that's going to be x squared plus y squared equals the radius squared, which would be in this case 25. Let's see. So we would have and I only have kind of enough space for a semicircle, so this will be, I hope that's about the same distance, 5. Semicircle, not too bad, a little bit parabolic, but semicircle. And then we're going to have a radius of the next one of 3 inches, which is nice. I think they picked that on purpose because a 5 and a 3 will give us a 4 with the Pythagorean triple. So let's see, radius of 3. I don't know, we'll just say that here this is the radius of 3. So that's kind of what we're boring out of the sphere. We're going to drill out the radius of 3. So all of this stuff in the bottom of that diagonal line, or that dotted line, is going to be gone. And the stuff that I'm going to rotate, not a highlighter. The stuff that I'm going to rotate is this bit here. So again, if we have one length of 5 and one length of 3, if the radius is 5, then they're going to intersect the two bits here. This is going to be at 4 and 3, and this will be at -4 and 3. And I know I may not be drawing it exactly to scale. Drill a hole through a metal sphere, so we have a sketch. The interval. Well, the interval is going to be useful to know which way I'm going to rotate it, but I guess if it's a sphere, I drew it horizontally, but there's nothing saying that you couldn't have done it vertically, so the direction that you rotate it really doesn't matter. Rotate around the x-axis or the y-axis. I kind of drew it where I knocked it out horizontally, so I'll rotate it around the x-axis, so that way I would have things solved in terms of y. So the interval, in this case, if I solve it in terms of y, I'm going to be going from -4 to +4, so that's my interval, -4 to 4. The outer radius, if I take the outer radius, so let's do that one again, I guess in blue. The outer radius is going to be this guy here, which is the edge of the circle. Okay, so the outer radius is the edge of the circle, which in this case will be a y value. And if I take the equation that I have for my circle and I solve it for y, that'll be the square root of 25 minus x squared. And the inner radius is going to be this segment right here, which again is a y value. And here equals y. And in this case, that's just the horizontal line, y is equal to 3. Okay. So let's go ahead and integrate this guy and see what we end up with. Let's see. So the integration again, volume pi, the boundary that we got, or the interval that we got, I should say, was from -4 to 4. So you know what I'm going to do? Instead of doing it from -4 to 4, this is going to be symmetrical, so I could do it from 0 to 4 and just double it. So let's try that. Let's try it from 0 to 4 and double our values because it will be symmetrical. And let's see if this is going to work out for us here. So the outer radius is the square root of 25 minus x squared, quantity squared, minus the inner radius, which is just 3 squared, and I'm rotating around the x-axis, so I'm going to say dx. And here, volume equals 2 pi 0 to 4, 0 to 4. And simplify, so that's going to just give me 25 minus x squared minus a 9 dx. I need more room going down. So we're going to have 2 pi integral from 0 to 4. And this one, if I combine my like terms, it's going to be 16 minus x squared dx. And that looks, I don't want to factor that. I mean, it looks like it's the difference of 2 squares, but I don't need to factor that. I need to integrate it now. So let's integrate it. So I'm going to say 2 pi, antiderivative, this is going to be 16x minus 1/3 x cubed from 0 to 4. And 2 pi, let's do our substitution. The 0 doesn't matter, which is the whole point. So I'm going to say 16 times 4 minus 1/3 4 cubed. And of course, I'm going to stop there because substituting the 0 doesn't matter. And let's see, 16 times 4 is 64. And 4 cubed is 64, so that'll be 64 minus 3. Yeah, get a common denominator here. So I'd have to multiply by 3. I need a calculator here. 64 times 3 minus, well, I'm going to subtract 64, so it's really just 64 times 2. So that'll be 128. 2 pi 128 over 3. So 2 times 128 will be 256 pi over 3. Ha ha. And we're done. And in this case, they're giving us units. So I would be remiss if I did not include my units, because they gave us units. In that case, it must be included in the answer. So there we go. That is how we interpret finding the volume of a rotated object using either the disk method, where we're looking at cylinders, or the washer method, where we're still looking at cylinders, but we have to take the difference of the bigger cylinder minus the smaller cylinder. But I hope this was useful, gave you a lot of good looks. Thanks for watching. Take care. Be safe. We'll see you soon.